Okay, here is the answers for the Year 10 end of year examination 2014. I'm going to simply go through this paper nice and quickly and show you how you get to the right answers. Okay, this is the first one. It's asking for a simple volume in centimetres cubed. Because it's in centimetres cubed, you keep these values locked into centimetres. So this one will need changing. 0.1 is 10 centimetres. Therefore, the volume, which is length times width times height, will be 10 by 6.5 by 8, which should get us to an answer of approximately 520 centimetres cubed. Right, where do we go next with this? It's given you the units, that's fine, but we want equation or substitution and the correct answer. Right, it's asking here to put around correct units for density. Well, density will be it's going to have a mass, not a weight, so you can rule that out, so it's a mass over a volume, so that must be the only one. What about the density? Well, density, rho, is mass over volume. We have a mass because up here it's 480 grams, so 480 grams. I like to keep the units in the equation, and then you know what unit is going to fall out of the other side. And we have 520 centimetres cubed. And that gives us an answer of 0.92 grams per centimetre cubed. 1 mark for the equation the correct way around, 1 mark for substitution, 1 mark for answer, and 1 for unit, and that's where you get the 4 marks from. Okay, second question. This is talking about around the topic of particles and Brownian motion. And it says here that pollen grains in water, the pollen grains are taking a random walk. What does this mean? Simply, we were looking for the explanation that they're changing direction. Constantly. If you were to look at a particle moving around, it can be random, but it's just moving in all directions. Good. Moving on then, it's understood that the water particles were causing the pollen to move around. Why did it take a century? Well, very simply because water was invisible. The water particles were invisible. Therefore, they weren't seen. Therefore, they weren't attributed to cause the particle to be shaking around. So, describe how it's able to cause Brownian motion. Well, simply, you're looking for this collision. So here's the particle. Water and the particle are colliding together. So you're looking for collisions between pollen and water, and that causes a change in direction. There are many water particles, and hence, they're moving quickly. So there's collisions between them. They change their direction. I suppose that's a little bit, that's not describing why the water particles are. That's describing more about the pollen itself. So we're looking for collisions between, they're moving quickly, or there's many water particles for your 2 marks. Okay, now, and this is the one you see more often in the lab. You see smoke particles, and smoke particles are moving around. Why is that? Well, it's because air particles are colliding with the smoke. Good, hopefully we've got 5 marks there. Right, here comes the next one. It's It's talking about the sperm whale that's going underwater. This is dealing with the gas law, so you needed to have a good knowledge of the equations. First of all, yes, so you're looking for Howard links. Pressure, density, gravitational field. Pressure is rho GH. That's a long derivation of it, but you've just got to remember it. Also, a trick is often, if you're not sure of the symbols, and quite a lot of people ended up writing water density or gravitational field strength, which is wrong, write out the words completely, and that might be more useful. Good. It's given you a technique here as well that's quite useful, is underline the important points here and then plugging numbers into the equation becomes much more easy. So you're looking to show that it's approximately 9,700 pascals, so therefore you're saying use the equation. Let's substitute in 1020 for seawater. We have G, which is 10, which I hope we all remember, times the 950, and that gives us something which is very close to, it's like 9690 pascals, which is approximately 9700 pascals. So what we're looking for is effective substitution and the correct answer, demonstrating getting the correct answer for the 2 marks. Okay, now this one should be super simple. It's the K is important. So killer means you're multiplying by 1,000. You'll be surprised at how many people got that wrong. Multiply by 1,000 for killer. Good. Boyles Law. Now you're talking about Boyles Law. Boyles Law is simple. P1, V1, P2, V2. Now, so long as you keep these two in the same units and these two in the same units, life is straightforward. But some people were trying to change this and convert it into meters cubed and so on. It was becoming an awful mess. Simply try and keep units consistent. That's the trick. So what happens? Well, normally, let's look at, let's see if any more data is given here. Good. So we're working on atmospheric pressure, which is taken from the previous answer. So atmospheric pressure, you know that there is a 4 meters cubed, let me put the units in, of lungs. It says here it's taken a breath at the surface. And at the surface we know that's the atmospheric pressure. Okay, then they've dived to a depth of 950 meters. And you know at 950 meters the new pressure is 9700123 V2. So therefore you rearrange to get the second volume. And you merely have this side of the equation divided by the other side, giving us something like 0.041 meters cubed. So you wanted equation or substitution, correct rearrangement and answer, and unit as well. Good. One assumption, well, all of these laws take place, are only correct if the temperature's the same. They're also only the same if the air is constant, or if you like, no air has escaped. They don't breathe out on the way down. Okay, then we have the anglerfish, the humpback anglerfish, and this is talking about what happens if he pops up to the surface. If they go to the surface, at the surface, the pressure is less. Therefore, the volume of lungs increases. And those are the 2 major marks I was looking for. And then you can be as descriptive as you like. Explosion, popping, and so on. Yeah, there we go. Not looking for too much explanation with only the 2 marks, just the 2 critical ones. Good, okay then, right. Coming swiftly onto electricity, we're now looking at a filament light bulb. You're looking to take a range of values of voltage and current to work out the characteristic IV characteristics. Now the difficulty here is most people probably just throw in a light bulb on its own. However, that would not be enough if that weren't there, because then the voltage across this would be constantly the same. What you need to do is you need to change the resistance of this, which in turn, in this variable resistor, which in turn alters the amount of current going through and therefore the voltage on there. Or you could argue that varying the resistance here alters the share of the voltages, so that is essential. You probably get one for the variable resistor, voltmeter and ammeter. Good, okay then, correct definition of a volt. A volt is a joule per coulomb. In other words, it's the amount of energy that's popped on. If this were 3 volts, for instance, then this would have 3 joules of energy on each coulomb. So it's the 1 volt is 1 joule per coulomb. Let's take Ohm's law, which links resistance. Right. I think you'd probably easier remember it as an equation. But bear that in mind, that when these are asking you to describe, say to yourself, imagine writing out the equation in front of you. So you can say voltage is directly proportional to the current. That's definitely going to get you 1 mark. You've just said that. The second mark comes from so long as the temperature is the constant. Because that's your second mark. Because remember, if the temperature of an atom changes, then that changes the resistance, and then it doesn't follow Ohm's law anymore. Just like this here. There we go, that's a characteristic IV curve of a light bulb. And why is it a light bulb? What's happening here? Describe the different changes. Explain why. So, if you're describing 4 marks, there's quite a lot going on here. And I would first, you ought to say to yourself that first there is a certain resistance. And it is low to start with. Remember, on an IV graph, the resistance is 1 over the gradient. So if the gradient is steep initially, then that means there is a low resistance. But you notice as we progress, we get a lower gradient, hence the resistance is increasing. So resistance increases as voltage increases. Okay, we've got 2 good points so far. Why is that? Well, the lamp is heating up. So remember, this light bulb, when you put lots of voltage through it, is starting to heat up. And that in turn causes the metal ions vibrate more, which prevents as much current flowing. Hence why there is this deviation from the current increasing. there's any of these four statements, but there's probably 5 there, but any of them are great to describe what's happening with the circuit. Right, next question. Okay, the diagram shows an arrow which the conventional current always moves positive to negative. So that's which way it'll be flowing through the circuit. The next question says, work out the current in the circuit. Well, 3 marks. We need to know that V is I times R. There's the equation, and a nice rearrangement, which is R is V over I. If it were asking that, but it's asking for I, which is V over R, we take the figures that we've got, 1.5 divided by 3, which gives us 0.5 amps. 3 marks. Equation, substitution, well, equation and substitution will be together, so let's say equation, substitution, one or the other. Answer, unit, definitely. 3 marks. Right, how do we connect a voltmeter? Well, you're asking a voltmeter about the cell. It should always be in parallel. So that's how we connect it. One connector before and one after, and you'll connect it in parallel. 3 amps, so what's the total charge that it passed through? Remembering to include the unit. Quite a lot of marks here, so let's not miss a step. So we have, right, charge. We've got a current. We've got a time. And therefore, we need our equation. Charge is current times time, which is 3 times 30, which gives us 90, and the answer is coulombs. 1, 2, 3, 4. Good. Remember, charge, coulombs. Again, E. Time is just adding another bulb whose torch would make it brighter. State which circuit would be brighter and explain why. Well, if another bulb were introduced, no, it says time is just adding another bulb to his torch would make it brighter, but he's not sure whether he should add it. Oh, right, series or parallel. Well, if it were in series, well, let's just draw these. If it were in series, then in effect the resistance has been doubled. And if the resistance has been doubled, then the current halves, and so therefore they will be less bright. So therefore the only other way of doing it is in parallel. So therefore in parallel what happens here is each bulb gets the same voltage across it, and the current through this one is the same as the current through this one, as if neither were there, and so therefore you've got more current flowing out of the battery. Good, so I suppose the answer is parallel, because more current flows. Stroke, same voltage across each bulb. Tick, tick. Straightforward. Okay, number 6, what are we dealing with here? Free body diagram for what's taking place. Now, these free body diagrams, we can get awfully complicated with this. But, simply, I know that air is flying past this, but the first one that's obvious is the weight. From the centre of mass, acting down. And it should be weight, not gravity. Gravity creates a weight, a force, which is weight. Also, we've got this one acting upwards, call it drag. I know we could flow it around the outsides, but it's much easier to do it from the centre. And they must be the same size. So the sizes are important. The labelling is important, and the direction is important. There is our 3 marks for our free body diagram. And then, which of the 2 balls will have a lower terminal velocity? Explain which one. Right, so one has less mass than the other one, so which one? Okay, so 2 ways to explain this, I suppose. One is, if you have 2 of these, but one is completely full and therefore has a greater weight than the other one, then in order for it to hit the same terminal velocity, and we know that drag is proportional to velocity, this one must be going faster in order to create that amount of drag. This one must be going slower to create that amount of drag. Good. Maybe that's the easiest way to think about it. So the answer is the light one will go at a lower terminal velocity. We could... No, let's leave it as that. Good. Okay, conducting an experiment. 2 marker points. This is moving at a terminal velocity. A length has been marked out, and we want to find out the velocity, which is constant. So therefore, you just need the simple equations of a distance divided by time, which is the length divided by the time. What do we need? Well, we need a ruler to measure the length and a stopwatch to measure the time. And then, so we need one of those, and the equation. Okay, here we go. Force, mass, acceleration. You either know it or you don't. Force is mass times acceleration. I remind myself that a force creates a change in speed, which is pretty much the same thing. That's how I remember it in my mind. Let's take a look at the numbers. What we have up here, we've got masses and velocities. So therefore, Damien's scooter, they both have a mass of 108 kilograms. However, there's also the person on it. Then we have the acceleration, which is 3.2. Therefore, the force is going to be 192 MA. 192 by 3.2 gives us 614.4 newtons of force. 1 mark, 2 marks, 3 marks. Good. Now, because you know that force is proportional to mass and proportional to acceleration, and they're identical scooters, if this is a constant, let's start that again. F equals ma. If you know that this bit is constant, then if the acceleration is less, the mass must be more. Hence, Andy's scooter is heavier because its acceleration is only 2.3 meters per second squared. So with a lower acceleration, it implies it's a much higher mass. So the answer is, it's got a lower acceleration. Okay. Minimum stopping distance will be increased. Well, when you've been boozing, the one thing that changes is reaction time. So therefore, if we know the stopping distance is equal to the thinking distance plus the braking distance, this part, which is the velocity times the reaction time has increased significantly. And if that's gone up, and that's the same, this has gone up. Okay, here is part 2, and we're carrying on the end of year exam for year 10, 2014, from question 8. We've got a data log that's looking at a velocity time graph, but at this point it all stops, and you're going to complete the velocity time graph. So it says deaccelerates 8 seconds to 10 meters per second. Okay, so where are we up to here? We're up to 1, 2, 3, 4, 5. So each of these is 2, 42, 44, 46. And then we plus 8 onto that, giving us 54. And we're going to end up at 10 meters per second after 8 seconds. So this goes down to there. And then there maintains the speed, because there's deacceleration. If there's a gradient, there's an acceleration, whether negative or positive. Constant velocities are straight lines. 6 seconds, takes it onto there. At 6 seconds, the car hits a wall and stops instantaneously. Donk. There we go. 1, 2 marks. Describe the motion from 12 to 26. So from 12 to 26, it's accelerating. Remember, this is a velocity time graph, so anything with a gradient is accelerating. 26 to 32, that's a constant speed. 34 to 46, it's deaccelerating. But the deacceleration is increasing. Initially, has a slight deacceleration, a shallow gradient, and then it picks up and it's getting a steeper gradient. So deacceleration is increasing. Good. What's the average velocity of the car in the 12 seconds? Well, average velocity is the fastest speed, final, minus the initial speed, plus the initial speed divided by 2. The average. We start at 0 and we finish at 14, so therefore 0 plus 14 over 2 gives us 7 meters per second. Determine the distance travelled in the first 12 seconds. Okay, distance equals the area under the graph, velocity time graph. So the first 12 we know that's 14. We're looking for the area in here, which is a half times base times height. A half times base, which is 12, times 14. Let's take that back, which is a half times 12 times 14, giving us 84 meters. Or if you want, you could have said that the distance is the average speed times by the time. 7 by 12, giving you 84 meters. Technique, answer, technique, answer. Okay, acceleration is the gradient of a graph. And we're looking between 12 and 26. Between 12 and 26, what's the gradient here? Well, we're looking at the change in the rise over the run. The rise is from 14 to 22. 14 to 22. And divided by 12 to 26. So that's how you work at the gradient, the rise over the run. Or in actual fact what you're saying is it's the change in speed divided by the change in time, which is the same thing as acceleration. So therefore, that gives us, oh, wait a minute, sorry, that was 20, it's on there, I thought that was the stronger line, so it's 20, careful there. So that gives us 6 over 14, 0.43 meters per second squared. Method, answer, units. Acceleration, meters per second squared. Okay, well, radioactivity now. It says it occurs when the nucleus of an atom is unstable. Hence, this is a nuclear process because the nucleus is happening. Alpha particles contains 2 protons and 2 neutrons. Okay. Gamma, dangerous. How are you safe with them? Well, lead-lined boxes are used to store it, and also when you do handle it, handle with tongs, so you're not touching the source. Okay, this should be quick from your general knowledge. Charge of beta is negative, positive, negative. Gamma is neutral or none. This is a particle. Beta is a particle, and gamma is a wave. Okay, we've got some counts. And how do you obtain those? Well, you obtain them with a GM or Geiger counter. So I should say GM tube or a Geiger counter. Why is the count rate decreasing? Well, the sample is getting smaller. This is the count rates per minute. Remember, if you had a large source, it's going to give out lots of radiation, whereas a smaller one gives out less. Good. Okay, then what do you... So how do we work this one out? We are saying that measured count rates... Well, there's a difference between here and here. Why the bother with the 2 columns, you might ask yourself? Well, the difference is because this is the corrected count rate, or that which is just from the potassium. This is from the potassium and the background. And the difference between all of those is 40. So therefore the background is 40 counts per minute. But here they're asking for each in becquerels, which is counts per second. So therefore 40 and the number of seconds in a minute is 60, giving you 0.67, rounded, of course, becquerels. 1, 2. What source of the background? Well, you just know this. Say cosmic rays, rocks in the earth, buildings, etc. Okay, beta decay. So hopefully you know what beta is. Beta is an electron. Electron has no mass, but it has -1. So and if you imagine these as an equal sign, 19 equals -1 by 20. Whereas along the top, 40 must equal 0 plus 40. Good. Okay then. Now we're on to an idea of half-life, showing how the count rate decreases over a period of time. Half-life is the time taken for the mass of radioactive isotope to halve, or the activity to halve. Good. One or the other. What about this half-life? Well, look, we can try this in lots of different points. We can start at 700. Half of 700 takes us to 350. I just paused there for a minute because that didn't look right, but then remember here, that's a false origin to that graph there. Anyway, follow that one along, and that gives us something like 40, 1, 2, 3, 4, 5 for the half point, so that's 1, 2, 3, 43 minutes. Let's try another one though, just to see whether we're right. Let's try 500, which takes us from 18, and half of 500 is 250. Well, it's off the scale, we can't see it. So we're going to go just for the first one. No, that wasn't very instructive. Okay, 43. That's good enough to get your mark. I'm just going to look for the difference between those two, and it should have come out to be 43. I obviously should have guessed that 43 plus that would have taken us beyond the scale. Okay then, aluminium being well, why is beta not suitable for checking 20 mm? Well, beta is absorbed by centimetres of aluminium. This is too thick and it will absorb it all. You won't be able to get a noticeable source through. So therefore you'd best use gamma, which penetrates further. And describe how this works. Oh no, bumps into the rollers and they begin to write sheets that are only thick. Okay, so if it's thinner, less radiation is absorbed as it passes through. So therefore the detector receives more, and then the rollers compensate by moving apart. And if the rollers move apart, that which comes through will be thicker, and then it will correct itself. Good. So now we have 20 milligrams of this stuff, and you are looking at, it's got 15 years later and it's got 5.3 half-lives. So 15.9 years. How many half-lives are we talking about? Divide by 5.3 years gives us 3 half-lives. Okay, first point. Okay, so 20 milligrams in one half-life goes to 10 milligrams. In another half-life, it goes to 5 milligrams. And in the third half-life, it goes to 2.5 milligrams. So your answer is 2.5 milligrams. Second half. It's less than 9 months. What will happen? Well, it starts to, so the source becomes weaker, quicker, so therefore the sheets start to become thinner, because the machines are thinking that, well, as the source diminishes and the signal gets less, it's thinking that less is getting through, so therefore it thins it out to compensate. Yeah, we shouldn't say radioactivity runs out there, we should say the count rate decreases. So therefore you need to recalibrate the machine more often. Okay, there we go, that's the end of the paper.